With that being said, a warm welcome to the Kiel Imaging Seminar. It, it is great to have you all here today. I'm very happy to introduce to you our guest speaker for the day, Mr. Matthias Guenther, Deputy, Deputy Institute Director, Fraunhofer Institute for Digital Medicine, MEVIS, Bremen, in Germany. It is the second time for Mr. Günther in KIS. Last year, he shared fascinating insights into his work and his colleagues' work on reconfigurable metamaterials. You can find this talk among previous KIS talks on YouTube. Just search Kiel Imaging Seminar. Matthias Guenther studied physics at the University of Heidelberg and did his PhD at the Cancer Research Center in Heidelberg on arterial spin labeling. After receiving his PhD, he joined Advanced MRI Technology, a company founded by Feinberg in California. Eventually, after a few years, Professor Günther returned to Germany to found his own company in Heidelberg, MEDRI, offering research services for image-based clinical trials. But he also continued his scientific career at the University Medicine in Mannheim. Before, in 2008, he became a professor at the University of Bremen and joined Fraunhofer MEVIS in Bremen as part of the management board. He is now Deputy Institute Director of Fraunhofer MEVIS with a joint professorship on MR physics. Before we start to the audience, please wait with your questions till the end of the discussion. And with that being said, Professor Günther, the stage is all yours.
Thank you, Maya, for this really nice introduction. Actually, it's the third try, or the second try to have this same presentation. So last time, I think half a year ago already, we tried to do it, and I lost my voice exactly that day, so we had to cancel it short term. But now I found my voice again, and I'm really happy to be here and to present an overview on arterial spin labeling, and also some of the applications we are using ASL for. That being said, ASL has grown so much, and as you've heard, I've been working on arterial spin labeling since 25 years or even longer. I started in the MR field with arterial spin labeling. It's a long journey from there and quite some developments. And if we want to stick to half an hour or 1 hour presentation, it's almost impossible to have a complete overview on ASL. So I will really pick only a few topics, and it's by far complete, and it's a pretty subjective personal view I will be providing. So also the applications, they are really a very small selection of what's possible. I will mainly stick to neuro applications, but we'll talk a little bit about other applications as well. In the last couple of years, there have been some white paper and gray paper activities which are summarizing the field of ASL with different applications. I listed them here. And I will provide a PDF of the presentation, so you can directly click on those links and get a really much better, more objective overview on ASL. One very quick disclosure: I received patent royalties related to ASL techniques from Siemens Healthineers. Of course, the presentation is as objective as I can. So arterial spin labeling, I already mentioned this quickly, has grown quite mature, and there are a lot of different variants which allow to pick different aspects of the physiological stage of organs. And here I'm just showing some of them. Of course, we can measure perfusion with it, but that's not all. We can also get some dynamic information. We can get some spatial information, which vessel actually supplies which vascular territory. In the past few years, there have been developments even going clearly beyond perfusion, and I will tick a little bit on those topics as well and try to explain or give you an understanding how this works. It's not only working in the brain, so I do have some images to prove that it's also working outside the brain. So I'm always amazed when I look at this multi-organ shot, which I acquired, I think, in 1999. It very nicely shows perfusion in a lot of different organs. So the technology is quite capable of measuring a lot of different aspects, but it has taken quite a while to get this closer to the clinics. And it's still not fully established in the clinics. Okay, let's start with the perfusion imaging part without using contrast agents, arterial spin labeling. What I already mentioned, while we are typically looking at structural MRI in clinical imaging, arterial spin labeling really opens up a new view on a subject, on a patient, by adding what I like to call a functional aspect, if this term wouldn't have been captured by the people looking at brain activity. We are getting an additional information which is looking at function instead of structure. And hopefully, since it's related to physiology and to perfusion, maybe being sensitive to changes at an earlier stage before any structural damage has been taken. To explain how arterial spin labeling works, I typically use this map of Germany, where we could just consider that we would get access to a GPS device, which is located in every car. So nowadays, most cars do have a GPS device anyway. Let's just pretend we are getting access to all the GPS devices which have been at one time in southern Germany, so in Bavaria and Baden-Württemberg. And then we could just follow where those GPS devices are going to. And most of them will stay in Bavaria and Baden-Württemberg, but some of them will be moving north. And they typically will do this by the larger roads, by the autobahns. So we will be seeing quite some autobahn structures lighting up. And if we're waiting a longer period of time, we will see that they are accumulating a little bit in certain areas. And you can see they will be accumulating in centers of interest where there is more activity. So you can see Kiel here, you can see Hamburg, you can see Bremen, and of course Bremen is more active than Hamburg, at least. And in Kiel, I guess you're really coming up and increasing. So I might have to improve on this depiction. Nonetheless, that's already the basic principle. I am looking at preparing GPS devices in one region here in Bremen and Baden-Württemberg, in Bavaria and Baden-Württemberg. And then I follow them over time and look where they are going. And of course, there will be a lot of GPS devices down here in Baden-Württemberg and Bavaria in southern Germany, which are not moving. So there I'm also getting quite a lot of signal down here. With MR, we are doing exactly the same. Here, Baden-Württemberg and Bavaria is located in the neck region, upstream of the organ of interest. And I would typically acquire two different data sets. One where I'm preparing the inflowing blood by inverting the magnetization, and one which I would call a control image, where I'm just not inverting the inflowing blood. Then over time, I will see that there's some of this inverted signal flowing into the brain region, into the region of interest, and sort of modifying the local magnetization there. And what I actually do is I'm looking at the difference with and without this preparation. And depending on the time, how long I wait between the labeling and the readout, I will either get the larger autobahns, the larger vessels depicted, or I will get the micro-vascular part where the labeled blood is actually accumulating and where the oxygen and blood water is exchanging with the surrounding tissue. Short inflow time means in a healthy subject on the order of maybe 500 milliseconds, and a long inflow time for 15 or 2000 milliseconds. I will come back to this later. This optimal inflow time differs from subject to subject. It typically becomes later with age, and also it is modified by different diseases. And I will comment on this again. This later. This labeling decays with a T1 relaxation of blood because, as I said, the labeling itself is inverting the magnetization or saturating, so modifying inflowing blood magnetization, which means that's a disturbance of the equilibrium state, and this disturbance will just relax back to the equilibrium state over time. T1 of blood is on the order of 15 to 1600 milliseconds, depending on which field strength you are looking at. So typically after 2 or 3 times the T1 relaxation of blood, it will be very challenging to measure any of your labeled magnetization, because it has decayed. And in addition to this, if we are looking in the brain, typically the microvasculature takes up no more than 3 to 5% of the overall volume, which means that the signal change I'm creating by inverting inflowing blood magnetization is on the order of 1%. So I'm looking at the difference of label and control image, which is on the order of 1%. And I'm looking at this 1% effect. That's what I want to measure. And that's the real challenge in arterial spin labeling, to really suppress or remove the signal of the static tissue and only get the signal of blood. There are different techniques which you can use to actually label inflowing blood. What I've just shown is the so-called pulsed arterial spin labeling technique, the parcel technique, where you have a pretty short labeling time. So you're just applying an RF pulse to invert the magnetization, and that's 10 milliseconds or on that order. But you are inverting the magnetization in a pretty large region. And then this inverted magnetization in this region will flow into the brain. That's a technique which provides pretty high labeling efficiencies, close to 1, and is a pretty robust and flexible design. But you have the drawback that since you label at one specific time, your magnetization will decay relatively quickly while it is flowing into the brain. And of course, the part from here into the brain is much longer than from here. So the later part of this labeled blood bolus will have seen quite some decay over time. One technique which overcomes this limitation is the so-called continuous ASL, or what's used nowadays most often is the pseudo-continuous ASL, which is not using a continuous RF pulse, but an RF pulse which is separated very quickly so that it appears or has a similar behavior as a continuous amplification or application of the RF pulse. And there we are using a physical effect which is called the flow-induced adiabatic inversion. Don't want to go into details, but what it essentially does is that blood flowing through a small slice will get inverted by being or by seeing several RF pulses. And this allows for a relatively long labeling time, so you can label over 2 or 3 seconds in a very thin region. So the labeled blood only has to fly from this thin region into the brain, so it won't decay that strongly. This technique is a little bit sensitive to off-resonance effects and other effects. I will also come back later to this. So some of the developments in the last couple of years try to make this technique less sensitive to off-resonance. So especially in the non-brain regions in the abdomen, pseudo-continuous ASL still remains challenging. Both pulsed and continuous ASL have the drawback that I'm labeling outside the brain or outside the region of interest. And then I have this relatively long inflow time to be able to get a signal close to the capillary exchange site. And one technique which is trying to overcome this is to say, okay, which property does our blood water actually have, which we can utilize to label? Here we are utilizing that. So here that the blood is in this region at a certain amount of time and then is flowing from here into the region of interest. For the pseudo-continuous, we are using the fact that that the blood is flowing through this slice and is being labeled. But in both techniques, we are labeling the static tissue signal in those regions as well. So we can't apply those within the imaging region. With the velocity selective, this technique says, okay, the difference between the blood water, which we want to tag, and the stationary spins are that they are moving, regardless in which direction. Yeah. So if we can just only label velocity or only spins which are moving, we are only getting the blood water labeled within the vasculature. And that would mean that we are much closer to the capillary exchange site, which we are really interested in. And that's the velocity selective ASL technique, which has become more major in the last couple of years. So there's some work. I won't comment on this in more details. If you're interested in this, please look up some of the recent reviews and overviews on this technique. For all techniques is that we are sort of isolating the blood signal from the tissue signal, and that we get images which depend on blood signal only. At least at the time of labeling, we know that our magnetization was in the blood compartment. And as I said, varying the time between the labeling and the readout part, we can capture different phases of the history of those blood water spins while they are traveling down the vascular tree. So that's what I want to show here. So depending on how long I wait between the labeling and the readout for pulsed or continuous ASL techniques, those times would be correct. For the velocity selective, I would rather start in regions here, so I can more or less skip the first 800 milliseconds and really concentrate on the microvasculature and small arteries and arterioles to get signal from. But here you can really get the different inflow phases, which turn into different parts of the arterial tree, of the vascular tree. And if you wait long enough, you can make sure that you are getting the vascular, the capillary exchange site down here in the vascular tree. And that's what we typically use. So this timing allows us also to time where we are in the arterial tree. And having an appropriate model sampling this inflow, we will get different sample points, different signal intensities, and then we can apply some models to this. And will be able to extract parameters of the physiological aspects we want to extract. So that's always based on a model, and I will also come back to the modeling aspect in a few minutes. First of all, I want to make clear that an important factor in arterial spin labeling, in my opinion, is to get this dynamic information. So to get the information at different inflow time points, which then allows you to apply an appropriate model to get different parameters extracted. And as I said, I will come back later. There are models which make a lot of assumptions, which also allow to extract perfusion based on very single, maybe on a single measurement or only on two measurements. But in my opinion, if you really want to make this work in a clinical setup, it's always important to get this dynamic information because there is a lot of information in this dynamics, and you will be missing them in especially in certain diseases. You will miss very important information for quantification of whatever parameter you are applying because most of the assumptions won't hold. So one point in my research in arterial spin labeling was to speed up the sampling of the different inflow times. Because I already said, if we want to invert our magnetization and we have to wait to read out our image, we have to wait rather long to allow our magnetization to recover, and then we can apply the next labeling stage. We can then wait a different period of time. That's something we have to do to get the whole sampling of our readout, which is extremely time consuming because we don't have to acquire one of those data sets only once, because I said we need to measure differences on the order of 1%. So our signal to noise has to be high enough to be able to see those differences of 1% between label and control. So we typically have to repeat each measurement quite often, which means that acquiring this data set for 10 different inflow times, it scales quite rapidly to scan times above 10 minutes. So what you can do instead is to say, okay, instead of acquiring one inflow time each measurement, we could apply several of them and not using a 90-degree flip angle for the readout here, but only using a smaller flip angle. And that's very time efficient. So in principle, you can get the whole time series in just one single shot. So in principle, if you would acquire data for 3 seconds, you have a label image, you have a control image, so you could get the whole inflow within 6 seconds in principle. And you can combine this to all gradient echo-based techniques. So flash, balanced SFP with some side constraints, spirals, whatever you want. It's just not possible to use spin echoes in combination with this what's called a look locker readout, because you need to have this small flip angle for the readout part to preserve some parts of your magnetization for the later readouts. That's what I said. You are somehow saturating your inflowing blood. So for the micro-vascular perfusion, that's typically underestimated. You can correct for it, but you're very quickly running into some noise amplification if you try to compensate for the microvascular perfusion in the very late readout phases. But where it is really strong is in acquiring this inflow process up to a certain vascular level. And I was using it quite a lot for what I call a dynamic angiography, or what's generally called a dynamic angiography. So using this technique together with a flash readout, you can acquire within 1 or 2 minutes on an 1.5 Tesla. That's where this was acquired. Vascular information in a very high temporal resolution So on the order of 30 milliseconds is what you can get here. And you can see subtle changes here, for example, before and after a surgery in an ICA stenosis case, very nicely see the delayed arrival of the blood coming from the MCA. And if you look carefully, you can even see the bypass here coming from the vertebral artery here. After surgery, you see it's already arriving at the same time. So the ICA signal is arriving earlier, but still the communicating artery is still open. But if you look very carefully, you can see that it's flowing from top to the bottom, so from the ICA down to the vertebra. So that's information which you can get very nicely with this look-locker technique. That's just another example for an arteriovenous malformation where you can very nicely get the feeding artery and the capillary exchange site and the draining vein here. And I always joke, so I create this image 20 years ago. I still don't know why I'm using blue for the artery and red for the vein, but yeah, I was young, and sometimes you do things you're not really thinking about a lot. Anyhow, if you want to combine this with spin echo readouts, and in the meanwhile, I was developing some technique which I won't talk about today as a readout approach. Instead of using EPI, I was using a 3D Grace sequence, which is a combination of an turbospin echo train and an EPI echo train, which involves quite a lot of refocusing pulses, so spin echo pulses. And with this, I couldn't use the look-locker readout. And believe me, I tried several times. So it's not working that well. So I thought, okay, how can I speed up the imaging process, still utilizing an efficient 3D Grace readout? And instead of having one labeling and several readouts, I thought, no, let's have one readout and several labelings. And I combined this with the continuous ASL. And if you remember, we need two images. One is in control phase where the magnetization is more or less in the equilibrium state, so +1, and one where I invert the magnetization where it is -1. And I just said, okay, I just use this continuous ASL, which labels over 3 seconds, and I split this into several sub-boli. And each sub-boli, so when I start with the labeling here, this one will flow in and will have a lot of time to travel down the vascular tree, while the one which I label last will reflect just this very early inflow time because it didn't have much time to travel down the vascular tree yet. And yeah. So what I did was to say I have to come up with a scheme which very efficiently tells me how does this label and control pattern have to look like for those different sub-boli. And there's one efficient way to do this. That's the so-called Hadamard matrix, which just is a binary matrix which has two different values, +1, -1, or 0 and 1. Where each of the patterns which is created are unique and creating different patterns for each subbolus. And what I actually get, I'm really running out of time, so I have to hurry. Sorry for that. So I have I just switch between control and label phases. In this Hadamard encoding, I have one readout, and then I'm getting images out where the labeled blood just has different or is reflecting different patterns. And it turns out I'm acquiring 8 different data sets here. And in using those 8 different data sets in different combinations, I can reconstruct each subbolus image by just subtracting where the bolus is on and adding this measurement where I have a control phase for one specific bolus. And by just looking at one bolus, so subtracting the first one, adding this one, subtracting this one, adding, subtracting, adding, subtracting, I can show that I suppress the signal of all the other boli and only get the signal from this particular. And so I can reconstruct all different inflow phases by just combining those 8 data sets in one run, which makes it much more efficient for the multi-TI P-Castle. I have to acquire one data set for each inflow time. For the time encoding, I'm acquiring 8 datasets, but can reconstruct 7, which means that for the multi-TI P-Castle, where I acquired separately, I have to acquire at least 14 different datasets to get 7 different inflow times. But with time encoding, I only have 8 for 7 inflow times. So that is already an advantage. But I'm adding up 8 measurements instead of 2 measurements for each individual inflow time. So I'm a factor of 4 times averaging more data. So I'm getting 2 times higher signal to noise by just doing this in a shorter period of time. And so it turns out that I can get the same signal to noise in 1/n, so 1/8 of the time. And one can show that you are getting the same results if everything works robustly, if you have no motion and all this stuff. Which makes it a little bit more complicated in practice. But nonetheless, you have a quite efficient way of acquiring different time series. And yeah, even running this in a clinical setup is something which we have done in the past. So I'm already pretty late and behind my schedule. So I won't dig too much into the modeling part, but just give you one very rough idea on how this looks like. The basic idea of the modeling is that we typically have a voxel, which is considered the tissue. We have an arterial input function, which describes how the magnetization is flowing in, and then something which describes what's happening within the tissue. And then we might also have some outflow of the signal. And then depending on how complicated the model is, which describes what's happening inside the tissue, we are getting more complex models, which allow us to also look at exchange processes between the microvasculature and the tissue. You can get even more complicated models. And as I said, the modeling is pretty simple if you do a lot of assumption. So if you put on a lot of assumptions, what you think is right, your model can be very simple. And once you start to throw away most of your assumptions, you can get very complicated models. If you are interested in the quantification aspects, there is this book by Michael Chappell and others describing the quantification. You can have a look there. And there's also a nice tutorial and explanation on the FSL website. So I will be skipping some of the features we have developed lately to make the measurement more robust, and now jump into the part of arterial spin labeling going beyond perfusion. So as I said before, coming back to the map of Germany. If we do have a GPS in every car, I said then we can follow our spins, and we know, okay, the spins have been, or the GPS have been down here in southern Germany at a certain time, and then they have traveled north. What we now want to do to extend, so that's how ASL works for perfusion. If you want to extend this, we just assume that we are also able to add a webcam to each car and see how the surrounding looks like of each car. And by doing this, we get an impression how the surrounding of the car looks like in different at different time points. In very early time points, we mainly get images of the Autobahn, so how the Autobahn looks like. But over time, we'll see where the car is ending up and how it looks like there. And that's what we are actually doing in arterial spin labeling as well, by looking at the at parameters which depend on the surrounding of the of our labeled blood-water spins. So I want to show you one example where we are utilizing the T2 relaxation time for measuring while we are reading out the image. We are measuring T2 or at different echo times, which will allow us to get T2 relaxation time of our labeled spins. So from those 1%, as I said, of the overall signal, we are now measuring at different echo times to get an T2, an impression of the T2 relaxation time. And what we can assume is that or what we can expect is that we will see different T2 relaxation times inside the vasculature and outside the vasculature. So we can start modeling this, that we do see changes in T2, which are based on the exchange of our blood water, the labeled blood water spins, actually going beyond the blood-brain barrier, so leaving the vasculature, going into the tissue. And by modeling this, because we only have not only have different inflow times, we also now have different echo times. It's a little bit more complex fit we are applying. But this allows us, based on this model, to distinguish between blood compartment and the extravascular compartment. And this allows us to model exchange between those two compartments, which in the end allows us to probe the blood-brain barrier as long as our model is correct. Yeah, as the disclaimer. And that's what we have developed and tried to make robust over the last couple of years. We were lucky to get some funding on this in the Joint Program for Neurodegenerative Diseases. That's the so-called DEBI project, which is an international project with quite a lot of different collaboration partners, which are listed here. Where we combined some technical developments, having some automated optimization, subject-specific optimization tools, doing some background suppression, which is optimized on an individual. Also estimating the optimal timing parameters, which is quite essential for doing in Alzheimer patients, because there the perfusion is really delayed, or the arrival is quite delayed, and also being able to do motion compensation and stuff like this. Sorry that I can't really get too much into details. If you're interested in this, you can either contact me or read up this stuff in the publications we published recently. As I said, I will provide this information as in PDF, so you can also look here at the first results in some cohorts looking at how the blood-brain barrier, or at least the exchange time, looks like in different regions of the brain. With this, I think I have to jump to an end so that we do have some time for discussion. I hope I was able to explain a little bit to you how arterial spin labeling works, give you some impression how this can be sped up, and how we utilized different technologies in the past, and what potentially can be done with arterial spin labeling. So not only measuring perfusion, but also going beyond. And I showed you this one example, probing the blood-brain barrier. What I missed to show due to time constraints is, or at least I want to say it now, we are implementing, or we have implemented this stuff in a framework which is vendor independent, called GammaStar, which we are also developing. Which is capable of running on different platforms from different vendors. So we do have implementations on GE, Philips, and Siemens systems, but the best coverage right now is still on the Siemens systems. We are working on Siemens, on Philips and GE implementations as well. But that's something we see as a pretty important step, moving this really into clinical trials, into a level where we can really make a difference in clinics with this technique, because I'm really fascinated by this technique. As you can see, that I'm working on this since 30 years, and yeah, have come quite a way, together with a lot of colleagues and a great ASL community. Thank you so far, and I'm open for questions.
All right, thank you, Professor Günther, for this brilliant talk. So, as Professor Günther just said, and now we enter the discussion part of the presentation. So, if you have questions, please feel free to ask. Perhaps in the meanwhile, I can ask a question. So with using ASL for blood barrier imaging, does this put more of a demand on the motion correction aspect of ASL?
Also, yeah, not only, but it's really tricky because ASL itself is already limited by by SNR. And then opening up another dimension with getting the different echo times, and then applying a model where you have a lot of different parameters doesn't make it more sensitive. So it is prone to a lot of different changes. Motion is one. But another effect is also that you're getting more sensitive to your model itself, where you have to prove all the different parts, whether they are real or whether they are describing what you want to describe as well. That's why I was a little bit hesitant. We are really right now in the process to show, are we really assessing the blood-brain barrier with this technique? Or could there be other changes? Because we are only looking at T2 changes. We just pretend T2 changes. There's also a technique looking at diffusion coefficients, because their assumption is that diffusion will change inside the vascular and outside the vascular. And those two techniques are not creating exactly the same results. So that's something we are right now really trying to understand. And our aim in DEBI was to apply it to neurodegenerative disease, to Alzheimer patients. And if you're working with Alzheimer patients, you might know or you are experiencing quite a lot of motion. And that's why I think motion is compensation is especially for this application an essential part. Right now, we are mainly doing rigid or a fine motion compensation. Once we are going into the abdomen, I think it will also be necessary to do a little bit more, either have a technique which allows for free breathing or do more elastic motion registration and compensation.
Thank you. Yeah, Stefan, please speak up.
Oh, my microphone should now be working. How robust is ASL in clinical routine, especially continuous ASL? How much depends it on the labeling plane if you have different technicians in front of the MR system?
Yeah, so you are really poking into a very critical point. Right now, at least the techniques which are provided by the manufacturers still depend a lot on positioning, on really knowing what you are doing when you are measuring. And in my opinion, that's the main point which makes ASL not robust enough right now for a clinical routine setup, because it is too user dependent. I think we will need approaches which adapt the scanning parameters, the labeling slice, some of the scan parameters automatically on a subject specific level. Otherwise, it won't make it into clinics. That's my opinion, and that's what we are working on. And I could fill another 2 hours on the ideas we do have, and we already implemented some of this in making this more robust, also in terms of positioning the labeling and optimizing it in terms of off resonances, for example.
Thank you.
Hi, I have a question about the glymphatic system.
Mm-hmm.
So you mentioned in one of the slides that we have this velocity ASL or velocity we can suppress or excite or invert space with a specific velocity of the capillary blood in the capillary. Maybe we will have in this case the inversion of the glymphatic system outside of the blood vessels. It's maybe a disadvantage of this method or an advantage of this method because we can have information about the glymphatic system using ASL.
Yeah, so for velocity selective ASL, you're typically labeling not too close to the stationary tissue spins. So you're typically looking at velocities maybe down to 2 or 3 millimeter per second, and you're not going below. And the glymphatic system typically has flows which are even below the 3 millimeter per second. So you're typically not labeling the glymphatic system with the velocity selective ASL. I think there have been some trials to do this, but the closer you get, or the slower velocities you want to label, you have to switch higher gradients, stronger gradients for a longer period of time. And this makes the technique very sensitive to motion, because if you do have motion during your labeling period, you have very easily velocities of the whole brain of more than 3 millimeter per second, which means that you would label the whole stationary tissues, tissue spins, which you don't want. And that's really tricky. Yeah. But there is work in utilizing ASL for the glymphatic system as well. But most of them are trying to go to very long echo times. Because if you do have, so you're looking at the exchange of the vascular system or compartment to the CSF compartment. And there you would be utilizing the very long T2 of CSF. So if you go to echo times of 300, 400 milliseconds, you are seeing exchange between the vasculature and the CSF.
Thank you very much. Yeah, and thank you again for the very nice talk. And maybe I can use this combined change in the diffusion coefficient using ASL, because I'm working on diffusion in my work. Thank you very much again.
Okay. Enjoy. I think it's fun.
So, any last questions? That doesn't seem to be the case. So with this, I would like to thank you all for joining this seminar. I would also like to thank our speaker for this wonderful presentation. And I wish you all a pleasant evening, afternoon, or morning, depending on your time zone. And until the next seminar.